Hello everyone, and welcome back to a new episode of Advent of Code 2016. We're going to be looking at my solution to day 15 today. Again, this is one that I've solved ahead of time. Could have done it on camera, but for reasons of I don't know, a lot of solving this puzzle is not something that I really did on screen. There's a lot of thinking about the math involved in this one, rather than just implementing the solution. And I think it's more interesting to talk about that than to watch me type out the solution. So let's do that. Day 15. Timing is everything. The halls open into an interior plaza containing a large kinetic sculpture. The sculpture is in a sealed enclosure and seems to involve a set of identical spherical capsules that are carried to the top and allowed to bounce through the maze of spinning pieces. Is this a link to, I guess, like a marble bouncing machine or a pachinko machine? Who knows? Part of the sculpture is even interactive. When a button is pressed, a capsule is dropped and tries to fall through slots in a set of rotating discs to finally go through a little hole at the bottom and come out of the sculpture. If any of the slots aren't aligned with the capsule as it passes, the capsule bounces off the disc and soars away. You feel compelled to get one of those capsules. I wonder if this is like some Easter Bunny magic or what. Like, I'm on a mission. Why do I want a capsule? The discs pause their motion each second and come in different sizes. They seem to each have a fixed number of positions at which they stop. You decide to call the position with the slot 0 and count up for each position it reaches next. Furthermore, the discs are spaced out so that after you push the button, 1 second elapses before the first disc is reached, and 1 second elapses as it passes from one disc to the one below it. So if you push the button at time 100, it reaches the top disc at time 101, the second disc at time 102, the third disc at time 103, and so on. The button will only drop a capsule at an integer time, no fractional seconds allowed. Okay, so the idea is we have a bunch of spinning wheels with holes in them, and we want to drop a thing so that it reaches the hole in all of them, and compute how long we have to wait before we first push the button. Where is our puzzle input, please? At the bottom here? Yeah. So I was surprised to see so few discs. I thought there would be more. And I think that the most important insight into this puzzle is not a super complicated one, but maybe one you could miss, which is that we're basically, well, gosh, isn't it interesting that all these numbers are prime? How convenient. But what we're being asked to compute is we have 6 prime numbers, and each one of them has a position. And also the discs, like the further along the disc is, you can sort of imagine the discs didn't move, or imagine there was 0 time for the ball to fall through all of the things instead of 1 time unit per disc. We would basically just be looking for what is the first number, or the lowest integer, that is equal to 12 mod 13 and equal to 10 mod 9, or I don't know exactly. The point is, we're basically being told, find a number which is equivalent to equivalent to n mod some prime, and equivalent to some other n mod some other prime, and so on. Both the disk's number and its starting position influence what modulo we're looking for. But you don't actually have to keep track of those two things separately. You can just say, all right, well, disk 1, it's at position 1 at time 0, but let's say we dropped the ball at time 0, right? It would have time to scoot forward by 1, and it would actually be at position 2 at time 0. If we dropped a ball at time 0, it would reach disk 1 at position 2, not at position 1. And for disk 2, if we dropped a ball at time 0, 2 time units would advance, and it would actually be at position 12. So we're looking for a number that's equivalent to 12, well, not 12, 19 minus 12, which is 7 mod 19. right? So we want a number that's equivalent to like 11 mod 13 and equal to 7 mod 19, and so on. We have this for each prime, for each of these numbers. And so let's look first at like the most, I thought, straightforward way you could possibly do this. And I was thinking it would be way too slow, and it turns out it wasn't, and I was kind of disappointed. So we have a parse function, and since there's only really one expression we need to match, and there's nothing complicated in it, I just use a regular expression. Remember, I had an episode somewhat recently about, hey, there's more ways to parse than just regexes, but this is a problem that regexes are great for. Small in scope, simple, no variations, no repetition, so great, a regex. And we parse out, well, the three groups are disk number, size, and its initial position. And we call the prime an int of the size, and the residue is what number we need to find. So we need to find a number that is equivalent to something mod the prime. And what that something is the prime number itself minus. So basically, it's if we dropped a ball, it would take first. It would take the initial position that we're given. What if we dropped the ball at time 0? What position would this disk be at when the ball got there? Well, that's int of the init plus int of the disk num. Okay, but we don't want it to be at that position. We want it to be at position 0. So we take it modulo the prime and subtract it from the prime. And that's the goal residue that we have. We want it to be equivalent to this residue mod the prime. And we just return a tuple. There was not much sense making a class to model this. We're just passing around two numbers. They don't have to do anything fancy. So we just return a tuple of those two things. And the only actual interesting thing that we have to do in this, so let's skip this prune function for a moment. So what we're going to do is just count up all the integers starting from 0 and get an iterator of all of those. And we'll remove all the ones that are not equivalent to whatever mod 19. So note, the algorithm is basically to arrange the wheels from largest to smallest so that we can remove as many candidates as possible before doing any future computation. So in our example, the largest prime is 19, and we want to be equivalent to, let's see, disk number 2 has 19 positions. At time equals 0, it's at position 10. So 12, right. So we need to be equivalent to 7 mod 19 is our first hurdle. So we just take all the integers, and any one that's not equivalent to 7 mod 19 we throw away. And then we go through the remaining integers, and the ones that are not equivalent to 11 mod 13 we throw away, or whatever. I don't think 13 is our next prime, but that's the idea. And we do that for all of the primes that we have, and the first number that doesn't get thrown away by any of them is our answer. So the way to do that is we start with a generator, an iterator. I never know which is which, what the difference is in Python. I just say whichever one I feel like. Of all the integers, and we have this prune function, which is given a prime and a modulo, remove all items from a generator that are not in that. And we reduce this pruning function, not actually over the ints themselves, but we reduce over all of our constraints that we're given. So we're iterating over all the constraints, and for each one, we're basically filtering the list of ints. And this prune is pretty simple. We just call itertools.ifilter, and it's a lambda of t, because that's the time that we're thinking of dropping the ball. And if t mod prime is equal to the residue that we want, then we keep it, and otherwise we don't. and then we just return that new pruned generator. And as I mentioned, we're sorting the primes so that we do the largest one first, so we can, like, imagine if one of the primes were 2. I don't know. It does turn out to be like a little bit faster to sort them in order than to sort them in the opposite order, but not as much of a difference as I thought. The real reason you might put the largest one first is because actually, like, if we thought about this just a little bit harder, we don't have to look at every integer, right? We could say, all right, well, I know it needs to be equivalent to 7 mod 19, so let's look at 7 first, and then let's look at 7 plus 19, 26, and then let's add another 19 to that and get 45. 45? Yeah. So we could do 1/19 as much work, but it turns out that, like, you don't have to do that. So I don't know why it's this easy. But even just doing the most I feel like they could have given us a lot more numbers, a lot more wheels. But okay, Topaz wants to make sure that these problems are approachable, even for new people, or inexperienced developers, I should say. Or perhaps not even inexperienced developers, but just people with a little bit less of a mathematical background. Okay, so fine, this works. And in fact, I can run it for you. Python source input, and it's 376,777. Fine, whatever. And so, as I mentioned, we can we could do the simplest optimization of just take the largest prime and iterate in steps of that size. But and that would make things 19 times as fast. Actually, hold that thought. Let's go look at the part 2 solution before we get into that. So part 2, the machine, whatever, it starts over, and it goes back to the initial condition as if it had been times 0 again, but it adds another disk with 11 positions that starts at position 0. That's right below the previously bottom one. Fine. So they just add one more disk. So what I do is I have this function called solve where I take the stuff that was in main and I do it up here instead. And all I do is I have the list of constraints and I solve part 1. It takes like no time at all to do it again. And then I just take the constraints and add one more string. Right? And this is also still like pretty fast. It's not lightning fast. It's like a second or 0.8 seconds or something. Let's time it. Okay, it's like 2.5 seconds. Part 1 is like 0.8 seconds. So, we could leave it there. But I was rather disappointed by this solution because I had been thinking about the first optimization, which barely even qualifies to be called an optimization at all. It makes things 20 times faster, but it's just so obvious that I was ashamed not to have implemented it. And I had been thinking of, okay, well, there's also a way that's relatively straightforward to implement to speed things up a little bit more. Let me, I'm not going to put it on screen here, but I am going to go find an email that I sent where I described what I was thinking of as an algorithm, because it has some a good example number that I couldn't think of just at the moment. So let's say we just had 2 wheels. A wheel, if we wanted a prime, if our prime is 5 and the residue is 2, so let's write this down. Let's say our constraints were 5, 2, And what, 11.4? Yes, that's a good one. So let's say we had this set of constraints. We could start at 15, or actually start at 4, why not? Because that's equivalent to 4 mod 11. And then just start adding and say, well, is that equivalent to 2 mod 5? No, 4 is not equivalent to 2 mod 5. Now let's add 11. We get 15. Is that equivalent to 2 mod 5? No, that's equal to 0 mod 5. Now let's add 11. And we get 26. Is that 2 mod 5? No, it's 1 mod 5. All right, let's add 11 again. We get 37. Is that 2 mod 5? Yes, it is 2 mod 5. And that could be our answer. And that's basically what the simplified optimization I was talking about would do. But I was thinking about this, and it seemed to me that there's a way to do this in without having to do all this silly iteration. Turns out I was actually wrong about that, sort of. Actually, completely wrong. But having thought about it was good. So what I was thinking was, okay, so I guess what I found is a solution that would happen to work for these 2 primes, but would not necessarily work for any 2 primes. What we could do is say, well, wait a minute. What is 11 mod 5? 11 mod 5 is 1, right? So adding 11, which is what we need to do to keep the larger wheel in the right position, is, from the point of view of the wheel of size 5, is the same as adding 1. Okay. So if we start at 4, and we see that we're not at the right place mod 5, how close are we to the right place? Well, if we were to add 3, we would go from 4 to 0 to 1 to 2, and then we'd be at the right place. So we could just add 3 times 11, and that's the same as adding 3 mod 5. So we don't even have to cycle through things, was my thinking. We could just, given these 2 primes, do a little bit of arithmetic, and immediately come up with what the answer should be. What is a prime? What is a number that satisfies both of these conditions? And well, I warned you that I was actually wrong. And the reason that I was wrong is because this is only easy if you have, I mean, it's sort of a known hard, I believe, problem to, basically what I was doing is implementing division modulo something. And I think this is something modulo like a prime number. And like I think it is known that this is kind of hard. Maybe what I was doing isn't division, but it's something like that, where the only way to actually do it efficiently is to just like iterate through all the possibilities. And it happened to be easy because I chose a prime that's equivalent to 1 mod another prime. But if I've chosen, like, say, 13, which is equivalent to 3 mod 5, it's not so easy to see how many 13s we need to add in order to add a given number mod 5. But, okay, so I thought I had this improved version. And it seemed to me that there must be some way. I couldn't figure out how to generalize this to more than 2 primes. But it seems like there must be some way, right? So what I did, actually, is I tried Googling, and I didn't know the right things to type in, and it was just not useful at all. But I sent an email to my sister, who's a mathematics professor, and I asked her, like, hey, I've got this problem. Here's a way that I think would work. It's really slow. And here's a way that I think would work that's faster, but I can't figure out how to generalize it for more than 2 primes. Do you have any ideas? Because this is very much a number theory kind of thing. And I took a number theory class like, gosh, how old am I now? I must have taken number theory like 12 years ago. And it was a very hard class for me. It was fun, but I definitely, I never went any further than number theory in that direction. Number theory and calculus are sort of like not the same branch of math. And so after number theory, I did some more calculus, I think. But it's not calculus is all about teeny tiny fractions of numbers, and number theory is like mostly about integers. And so they have very different kinds of things you need to learn. And I never really got much past number theory. I kind of made it through number theory, although I don't remember how. It was fun but hard. Anyway, so my sister said, yeah, it sounds like you might want the Chinese remainder theorem. And I was like, God, every single time something comes up in number theory, the answer is the fucking Chinese remainder theorem. What does this thing do? But I don't know. I looked on the Wikipedia page and I couldn't figure out like what it was like. It was describing what go ahead and look it up. I'm not going to show it on screen. Am I? Nah. It was describing some stuff that seemed like related, but I couldn't figure out exactly how it was relevant. But I looked at it again later, and I got to a part that said, like, induction based on the number of primes. And for some reason, even though this must be like, of course, induction. What else would you use? It's like the only way you iterate through things in computer science is basically induction. But as soon as I saw that word, I was like, oh, I figured out how to combine the things. I'm not sure exactly why, because the description going on the Wikipedia page did not seem very helpful to me. But I don't know. I also read some people on Reddit talking about having solved it with the Chinese remainder theorem. Maybe I got more information from that than I realized. But I guess what was the key to me was I was noticing, oh, I thought there was this closed form thing where you can just like get the mod of one prime take one prime, mod the other, and then just like basically do a division is what I was doing. Realizing that you can't do that, you have to do the iterating. You have to start at 4, then add 11, check if it works, add 11, check if it works, add 11, check if it works. Realizing that you have to do that, it suddenly became clear to me how to actually solve things. And before I show you, let me describe to you what the algorithm looks like. The idea is we have these two wheels here, right? And we start at 4. That's no good. We add 11. 15 is still no good. Add 11. 26 is still no good. Add 11. 37 is fine. Okay. And then what we can do is we now can say, all right, well, 37, we can turn this into a list with just one prime in it. 5 times 11, because we found out we need to be mod 37 of, well, okay. This combination of two wheels is going to repeat its position every 55 time units, right? Because they're kind of going to be spinning around independently, but there's only 55 total combinations of ways these wheels can be, and so after 55 time units, they'll have used all of those up, and they'll go back to their previous position. So what we can actually have is say, all right, we have just one prime. We can pretend we have a single wheel of size 55, and we need to be mod 37 of that single wheel. Once we've done that, we can use the same algorithm we did a minute ago and combine it with this larger sort of pseudo wheel that we've invented. That's a combination of the first two. So we're combining each pair of wheels into one larger conceptual wheel that we can use then to aggregate the next wheel, and the next, and the next, and the next, and so on. So that's the idea. What does the solution look like? Well, what it looks like is this combine function, basically. It takes two primes and two modulo, one for each prime. And it starts with a number x to be equal to n. So we have to be in the right we have to be synchronized with the right prime. And then we take x mod q and we see if it's the right thing if it's what Q wants. Is it M? If it is, then great, we found an answer. If not, we just add P. Wait for the first big wheel to finish spinning and get back to its initial position, and then check if the second wheel is also lined up, basically, right? And we just keep doing that, waiting through one cycle of the big wheel, and then checking the small wheel. Except that we're not actually doing it with iteration over a bunch of time units. We're doing it with addition. We're doing it by adding P rather than just waiting through P time units. And then once it's succeeded, we return a new wheel, which is multiply together the two existing wheels and use the new combined modulus that we want. And so now solve, we're just reducing with combine all of our constraints. And I sort them, but I don't know if that actually matters. And I return the element at index 1 in the tuple, which is the second element of the tuple, which is the modulus that we want. So we don't really care how big the gigantic wheel of primes is. We just care what modulus we have to be with regard to it, because we're starting at 0. And so we just parse all the constraints, and we solve them. And then we solve adding that other constraint. So main hasn't changed, but the way that we solve has. And indeed, if we time it, we're now done in a 20th of a second. Much better than 2.5, right? So this scales to much, much larger inputs than are given to us, basically. Because for each prime that we're given, we basically just have to cycle through, on average, half as many numbers. Like, if we're given a prime, if somebody adds a new wheel, we have to cycle through, on average, half of the numbers on that wheel before we find an answer. An answer that combines it to the previous ones. And so, great, that's good, right? I mean, you might have to do a lot more work. You would have to do a lot more work if you were doing it the way that we were at the beginning of the video, by iterating through each time unit. The goal, the convenience of this approach is that we sort of abstract over the concept of waiting for all the wheels that we have gotten to. All the wheels that we've already solved, we can wait for them all to cycle with a single addition operation instead of with thousands of modulus operations, right? Which makes it considerably faster. And it scales to much larger inputs. And so there's I was not the only one to figure out this Chinese remainder theorem thing, but I'm pleased with myself for finding it. I was considerably disappointed. Is that a good usage of considerably? Maybe. I was considerably disappointed to find that the dumbest approach I could think of was fast enough. I was hoping that I might have to do something a little bit clever here. On the other hand, there have been other puzzles where I have been disappointed that the dumb approach I thought of was not fast enough, right? Where it seemed like it was, A star search should be good enough for anything. Why should I need to prune the search space, right? Whereas here, I don't know, the dumb thing just seemed. I guess I felt like A star, by implementing A star, I had done a lot of work, and I was disappointed that it was not good enough. Here, the really dumb thing didn't feel like any amount of work at all. And the way of combining things was pretty cool, and so I was hoping it turned out to be necessary. But I think it's reasonable that it wasn't. I would have liked it, I guess, if going through things one time unit at a time had been inconveniently slow, and going through them 19 time units at a time had been good enough, say. But okay, whatever. So that's it for this puzzle. Yeah, done rebasing. Very good. I hope you guys enjoyed this solution. This multiple solution, right? We solved it twice, once, and really a third way that we talked about, but didn't actually do. Of what am I saying? of just combining the first two wheels, but not figuring out how to combine any wheels after that. That would have already been by itself been a bit of an improvement. But I didn't actually solve it that way. I solved it the dumb way and then waited for an email from my sister and solved it the good way. Anyway, that's all for this one. Hope you guys enjoyed. Thanks for watching, and I will see you next time.